Example 1.2.9, the pump used in the previous example, 1.2.7, is 75% efficient. So how much electric power are we going to be drawing if we want to operate this pump? So we're going to write our givens. The first is we were told what the efficiency of the pump is. From the chapter, we were introduced with the symbol eta. Looks like a cursive N almost, but it's the Greek symbol eta for efficiency. And that's 75% or 0.75. So that's the information we were given here. We need more info to solve this problem though. We got to go back to the previous example 1.2.7 and we got to know that the amount of work done was 588 kilojoules. So we also are going to need to know the amount of time that work was done in, and if you recall, that was 5 minutes. So that summarizes our givens. So what is it that we're asked to find? What are the required? Well, we want to know what the power into the pump is, right? How much power is the pump consuming itself? So we want to determine the electric power input into the pump. Now, what we know is the work done by the pump, which is its output power, or we can calculate output power from it at least. So what we want to know is the pump's input wattage, but that implies, because there's an efficiency, that we actually have to know what the output power delivered by the pump is. And so that is kind of a hidden required in this problem is, yeah, we need to know the electric input to the pump, but to be able to calculate that, we have to know what the power output by the pump is to determine the work efficiency. So the next required is what is the power output of the pump based on that efficiency. Okay. So that brings us to the solution method. How we're going to approach this is we want to calculate what the power output of the pump is, and we can get that from work. So remember that the definition of power is the rate of change of work with respect to time, or how much work is done in a period of time. Work, remember, is in joules, time is in seconds, and power is in joules per second, which we call a watt. So our work done was 588 kilojoules. That took us 5 minutes to do that. So that is our power calculation. We have to know something about units though, because joules per minute isn't watts, it's joules per second. So we need to convert that 5 minutes over into the equivalent number of seconds. We do that by multiplying by 60 seconds per minute. And what that will do is that'll give us joules per second by throwing that 60 into the denominator there. We find out that the output power of this hydroelectric pump that we're using, or this electric pump that we're using to store water, is 1,960 watts. Another way to say that would be 1.96 kilowatts. So that's the output power of the pump that we got from dWdt. That's not what the problem asked for though. We wanted to know the input power, and remember the relationship between work in and work out, or power in and power out, is that the output is always equal to the input times the efficiency. So here I've just rearranged that to say that the input power is equal to the output divided by the efficiency. So 1,960 watts divided by 75% efficiency gives me an input power requirement of 2.613 kWh. Sorry, I kind of blacked out there, but I think you saw it there.